In this video, we're going to take a look at polar coordinates, which are a particularly useful and specific type of parametric equations. You hopefully have seen this before. It's covered in most trigonometry classes, but if you haven't taken trig or it's been a long time, hopefully this will be a pretty good quick refresher for you. So the idea is that in our normal coordinate system, when we're doing Cartesian coordinates, we are essentially using two different lengths to define a point. So Cartesian coordinates, they use two lengths to define a point in 2D space. So to define its location. In 2D space, there we go. So the first length is how far you need to go in the horizontal direction, so the x-coordinate, and then the second length is how far you need to go in the vertical direction, so the y-coordinate. So the two lengths are literally the x and the y coordinates. X is equal to basically a length, and then the y-coordinate is essentially another length, or a distance. In this case, x is the length from the y-axis, y is the length or distance from the x-axis. Polar coordinates only use one length. And the other value they use is an angle. So these use one length and one angle to define a point. The length that we're going to use is r, and it's the distance from the origin. And then the angle theta is going to give us what direction we need to go relative, again, to the positive x-axis. So essentially, instead of saying go 2 units in the x direction, 3 units in the y direction, we'll simply say go 4 units in the direction of this particular angle, and it'll get you to a given point. So if we draw the picture, it makes more sense. If these are my x and y coordinates, and this is the point I'm interested in, the point x comma y, what that means is to get to that point in Cartesian coordinates, we go a distance in the x direction, so this distance, and then we go another distance in the y direction. In polar coordinates, we're going to go just straight to the point, a distance r, out in this direction, and we're going to pick that direction based on this angle theta. So that is the relationship. And if we use this and recognize that this is a right triangle, we can figure out relationships between these things. So one of the relationships, for example, is that if I look at the sine of theta on this triangle, so sine is opposite over the hypotenuse. That means that I get sine of theta is equal to y over r. And I can use that to solve for y by multiplying both sides by r, and I will get that y is equal to the r times the sine of theta. And if we do the same thing with cosine of theta, which is the adjacent over the hypotenuse, I will get x over r. So again, this is from SOHCAHTOA. And I can solve that for x to get that x is equal to r cosine of theta. And so I essentially have a way of prescribing my points, x and y coordinates, in terms of the polar coordinates r and theta. So these are going to be really, really useful identities that allow us to determine an x and y coordinate given r and theta. Similarly, we also know that because this is a right triangle, the Pythagorean theorem holds, and that tells me that the length of this side squared plus the length of this side squared will equal the length of this side squared. So we also know that x squared plus y squared is equal to r squared. And similarly, we know that the tangent of theta is equal to y over x, which if we solve that for theta by taking the arctangent, we can get that theta is equal to the inverse tangent of y over x. So, and similarly with this one, if I want to solve for r is the square root of x squared plus y squared. And technically there's a plus or minus sign here. More often than not, we will by convention pick the positive, but there may occasionally be a reason that you want to use a negative value of r. But these give us what our polar coordinates r and theta are in terms of x and y. So just to give you a quick review of how this all works, let's look at some examples. So I want to plot the point in Cartesian coordinates, which is root 3 comma 1, and convert it to polar. So here's my x and y coordinates. Root 3 is about 1.7, so if I call that 1 and that 2, then 1.7, which is root 3, is right about here. And then a height of 1 will be right about here. So the point I'm looking at is right about there. This is the point root 3 comma 1. So root 3 in the x direction, 1 in the y direction. I need to figure out this distance r and this angle theta in order to write this in polar coordinates. So to find r, I know that r squared is equal to the square root of 3 squared plus 1 squared. And that will give me, in this case, 3 plus 1, which is 4. So now that I have that r squared equals 4, this implies that r is going to be equal to 2. Let me fit it all on one line, just for the sake of ease. So r is equal to 2. It could also be negative 2. That is also a valid number we could use, but the positive number is going to be the easier one to deal with in this case. If it was going to be negative 2, I would want to actually figure out what the angle is going out this direction, and then figure out that I want to go negative 2 in that direction, which would bring me back to the point that I started at. So instead of going 2 in this direction, if I went negative 2 in this direction, it would put me back at the point that I'm looking for. But we're just going to stick to the positive version, which is what you should be doing 99% of the time as well. The second thing that I need to do is figure out this angle theta. And so we have our equation up here that essentially says that the tangent of theta is equal to y over x. So for us, y over x is going to be 1 over root 3. And that implies that therefore, again, theta is the inverse tangent or arctangent of 1 over root 3, or root 3 over 3. And you can plug this into a calculator, or you can also just recognize kind of by observation, if you know your unit circle well enough, this angle right here, if I were to just divide both of these numbers by 2, I would get a similar triangle with the same direction for this. And these are the coordinates of the angle pi over 6. So it's a matter of, again, plugging into a calculator or remembering your unit circle. So let me come in and delete those little pieces I just added. Okay, perfect. So we get that r comma theta, the coordinates in r theta and polar coordinates are going to be 2 comma pi over 6. But I mentioned, and I shouldn't re-mention, that I could have used negative 2 for the r. And the point is, this is not a unique representation. Polar coordinates are not unique. What you need to remember is that when you're dealing with polar coordinates, angles repeat themselves. Basically, in 0 to 2 pi, I can go all the way around. But instead of doing just from 0 to pi over 6, I could also write this angle as go all the way around plus an additional pi over 6. So all the way around would be 2 pi plus an extra pi over 6. That would also be an angle of 13 pi over 6. That's the same as pi over 6, or 13 pi over 6. Or I could add another 12 to that and get 25 pi over 36. I could also, again, like I said, go in this direction, which is what? That's going to put me at 7 pi over 6 and do -2. So I could have done -2 comma 7 pi over 6. That's another representation. Or I could have done +2 and that 13 pi over 6. But in general, we don't need these extra ones. All that's important to remember is that this representation is not unique. Similarly, I could go sort of in the reverse direction. I could give you the polar coordinates. So plot r theta equals 4 comma pi over 4 and convert to Cartesian. So just to be clear, up here, this was sort of x and y equals that. Now I'm giving you the r and theta coordinates and asking for you to convert to Cartesian. So we start by plotting it. If we can plot it, it makes it easier to kind of check our work. The angle pi over 4 is a 45-degree angle. So we're going off in this direction somewhere. And how far are we going? We're going a distance of 4. So that distance needs to be 4, and this angle is pi over 4, 45-degree angle. And I want to figure out now what are the x and the y coordinates to that particular point. And to figure that out, I can use these equations right here. If I know what r and theta are, I can plug them into these formulas and it'll spit out my x and y coordinates. So I know that x, which is equal to r cosine theta, just to remind you, in this case is going to be equal to 4 times the cosine of pi over 4. And y will similarly be, which is r sine of theta. So always remember cosine goes with x, sine goes with y. But sine will be 4 times the sine of pi over 4. And again, you can either plug these into a calculator, but really these are ones that I hope you know off the top of your head, that you remember from your unit circle. This number here, the cosine and sine of a 45-degree angle, that's a right angle there, that was a right angle up there. This is going to be root 2 over 2. So I'm going to get 4 times root 2 over 2, and it's the same for sine, 4 times root 2 over 2. And we can do a little bit of cancellation to get 2 root 2 and 2 root 2. So the coordinate we get is that xy is equal to 2 root 2 comma 2 root 2. So really, at the end of the day, these are a matter of, do you remember the unit circle or not? If the answer to that is no, it's probably worth brushing up on. You don't want to have to jump to your calculator every single time to plug in these values. You want to be able to just know some of these off the top of your head. Okay, so how are we going to use it? We're going to use these by looking often at things that we'll call polar curves. And we want to be able to deal with the geometry related to these polar curves and eventually do calculus on these polar curves. So these can be written, if we're dealing with a polar curve, as functions. Hopefully, more often than not, they'll be able to be written as functions that look like this. R equals some function of theta. Or, more generally, and it's totally possible to get curves that are not functions, as some f of r and theta is equal to 0, equal to a constant in general or 0 in particular. We can write it that way. basically, the curves simply consist of all points that satisfy that equation. That's kind of the definition of a curve related to the equation representing that curve. The curve consists of all the points that solve or satisfy the equation. And this isn't unique to polar curves. That's the idea, again, behind all curves and the equations representing those curves. Simply all the points that satisfy that given equation. So let's look at some common ones and hopefully get a sense of how we can use some of these things. So for example, what if I just said theta equals pi over 3? Well, for one thing, this is definitely not the form of this particular function that we've got here, right? It's not r equals some function of theta. There's no r at all. Instead, this can be written in this form. We could instead write it in this form, theta minus pi over 3 equals 0. And now it would be written in this particular form here. Some function that involves both r and theta. In this case, there's no dependence on r. It's only theta equals 0. So if we graph this, all it's saying is there's no restrictions on r. R can be whatever you want. We're still graphing it. Notice in the xy plane. So I'm still graphing it in the xy plane, but all we're specifying is what angle. Any r you want at this particular angle. And in this case, the angle is pi over 3, which is a 60-degree angle. So that goes about in that direction, but it can also have, as we said earlier, negative r values. So it can go in that direction as well. All we need is that angle right there is pi over 3. So this looks like a function to us in terms of x and y, and in terms of x and y it is a function, but it is not a function in terms of r and theta. I'm not plugging in a specific input and getting only a single output. I'm plugging in this one input and there's no restrictions on the output of r in a sense. That's why it doesn't fit this form. It can only be written in this form because it's not a function in terms of that. Again, there's many different r values for this one particular theta value. If you think of r values as just distance from the origin. So here's a point, here's a different r value, here's a different r value, here's a different r value, here's a different r value. Hopefully you can see these little dots I'm drawing. They're all different r values for the same theta value. So it's not a function. Okay, but that's what the graph looks like. So if you have theta equals a constant, it is a straight line going through the origin with that angle defined, that angle in reference to the positive x-axis. That's where we measure that angle from. So theta equals a constant is a line through the origin. Next one. What about r equals a constant? R equals a constant. If we remember what r is, we just said that r is equal to x squared plus y squared. So in this case, or r squared rather. So again, all I'm doing is coming back up and referencing this formula right here. Or alternatively, we could look at this one here. So x squared plus y squared equals r squared. So if r is equal to 3, then I could just square both sides of this to get r. Let's do it that way. Maybe this will make more sense. So I can square both sides to get r squared equals 9. But what is r squared equivalent to? R squared was equal to x squared plus y squared. What is that the equation of? That's a circle of radius 3. And again, I'm not going to draw this very well. Circles are for some reason very hard for me to draw on this tablet. But 3, 3, there's my y-axis, my x-axis. R equals 3 says there's no dependence on theta. But whatever theta direction you pick, you want to go out in this direction, you need to go a distance of 3. You want to go out in this direction, you need to go a distance of 3. You want to go over in this direction, distance of 3. Down here, distance of 3. So just tells us to pick all the points a distance of 3 from the origin. So r equals a constant, origin. R equals a constant is always going to just give you a circle centered at the origin. What if we do this one? R equals 2 cosine of theta. So now we finally got one that looks like this particular function here. It involves both r and theta. What does this thing look like? So, you will recognize some patterns. If you've taken trig recently, you may even remember what this looks like. But if you haven't taken it recently, here's a really easy way to figure these out. Well, maybe not easy, but the most intuitive way, in my opinion, to figure these out. The first thing I'm going to do before I draw in my xy coordinates is I'm going to draw in the r theta coordinates. So this is not the graph I'm interested in, but I'm going to use it to figure out what the graph looks like over here in the x, y coordinates. So this graph in r theta space, you could think of this as playing the role of your y and your x if you wanted to, but not for this graph, just for this graph. R is just the vertical direction, theta is just the horizontal direction. And as far as this is concerned, this is just the graph of a cosine with an amplitude of 2. So what does the cosine function look like? If it has an amplitude of 2, that means all of the oscillations have to occur between a height of plus or minus 2, has a period of 2 pi, and it starts up at the top, goes down through this point, goes down to here, back up to here, back up to here. And so it's going to look like this. And it would continue on in that direction, it would continue on in this direction. But this is what it looks like. This is just a traditional cosine curve, the one that you're accustomed to seeing, because we're using, that's what it looks like in r theta space, where theta is the input and r is the output. But what does it look like when we convert this over here to our x and y space? So what we need to do is think about exactly what's going on here. Right here, we're at the point where theta is equal to 0. So I want to keep in mind what values of theta we're looking at for each of these pieces. So over here it's 3 pi over 2, so on and so forth. And maybe we can even kind of estimate here, halfway in between, that's going to be pi over 4. Over here, that'll be 3 pi over 4, etc. So maybe we can go even in increments of pi over 4 instead to make it a little easier. What does that look like over here? Well, essentially what we're doing is trying to track down what the value is in any given direction. So when theta equals 0, the radius is 2. But over here, what direction is theta equals 0? Well, we already said that theta is the angle measured right here, angle from the positive x-axis, if you can see that. Theta is the angle as measured from the positive x-axis. So coming back down here, if the angle is 0, that means I'm on the positive x-axis. And I'm going what distance from the origin? I'm going out a distance of 2. So right here, this point, that is the point r equals 2, theta equals 0. If we move to theta equals pi over 4, so in our graph over here, that is up in 45-degree angle direction. So that is pi over 4, the direction. How far do I need to go there? Well, if I look at this, what I will find is it's about this height right here. Just ballparking it, it looks like it's going to be greater than 2, less than 2, greater than 1. I don't know, maybe 1.5-ish ballpark. Let's just say that's close enough, so about 1.5. And if we trace out radially, So here's what it would look like if we stayed at a constant distance of 2. We would stay along sort of a bullseye shape here. So circle in that direction. Here's what it would look like if we stayed out at a distance of 1, and so on. But we are at a distance of about 1.5. That puts us ballpark over here-ish. So in this point, I'm at r is maybe, 1.5-ish, somewhere in that ballpark. And theta is pi over 4. So I've translated this point. We could actually plug it in, the cosine of pi over, the cosine of, yes, that's what we're doing. Cosine of pi over 4 is root 2 over 2. When I multiply that by 2, we get root 2. And root 2 is like 1.41-ish, something like that. So I guess I could even write that in. Really, the number we're getting is not about 1.5. It's really exactly the square root of 2, which is approximately 1.41, I guess. If we go further, by the time I get to the angle theta of pi over 2, what is the radius? What is the height of my curve? It is down to 0. And so when I'm pointing in the direction straight up, which is pi over 2, my radius is down to 0 when I point straight up. So the idea is, over here, r is equal to height, and theta is equal to basically the how far left or right. What we often think of, so horizontal coordinate. So that's what we've got over here, right? R is the vertical axis, theta is the horizontal axis. So all I'm doing is translating an r theta coordinate from this graph, where r represents height and theta represents the horizontal coordinate, over to here. I'm taking that same r theta value, but now theta represents the angle as measured from the positive x-axis, and r is the distance from the origin. So I'm taking this graph and I'm shifting the definition of what I'm calling r and theta. Over here, r and theta are just essentially the horizontal and vertical position on this graph. Over here, they're what we normally think of. They're measured, the angle measured from the positive x-axis, or the radial distance from the origin. And we could do some other values in between. And what you wind up with, after it's all said and done, this is done poorly, but the next one would be down here, is we wind up getting a shape that looks like this. If we play connect the dots, going in this direction. This is the direction that we're traversing. And so that happens by going from here all the way down to here. So again, we got to pi over 2, and that gave us this point. So this point right here, that occurred at r was equal to 0 when theta was pi over 2. And I just picked that by picking this point right here. So I'm picking these points. I'm going to do these in color, just maybe it'll help some people kind of keep track. So here's like the red corresponding to red. This blue point here corresponds to this blue point here. The green point here corresponds to this green point here. And if we continue on further, maybe I'll have to pick a new color here, yellow. If I go down to, say, 3 pi over 4, that'll give me this point right here. It turns out that number right there, when I plug in 3 pi over 4, the cosine of 3 pi over 4 is negative root 2 over 2. I'll multiply that by 2 and I'll get negative root 2. And that's going to correspond to this point here, which is funny because I'm going in this direction, right? This is the direction 3 pi over 4. 1 pi over 4 gives me 45 degrees. 2 pi over 4, 3 pi over 4. So I'm 45 degrees this way. But the distance I'm going is negative root 2. So instead of going out this direction, that's why I have to reverse course and go back this direction. So this is really the point that r is equal to negative root 2, whereas theta was equal to 3 pi over 4. 3 pi over 4 points off into the second quadrant, but the radius is negative there, so it winds up putting this dot in the fourth quadrant. I have to reverse direction. And that gives me this point here. And then by the time I finally get down to, let's do purplish color here, by the time I get all the way to pi, the radius is down to -2. The direction of pi is this direction out in the negative x-axis. So that is pi, but how far do I need to go? I need to go -2. So I'm pointing this direction, but I'm going -2, which means I really wind up over here. So this purple point is the same as the red point where we started. The purple version of this point corresponds to r equals -2, theta equals pi. And what we get is a circle oriented along the x-axis. And it turns out normally to get around this circle that's centered on the origin, we have to go from 0 all the way around to 2 pi, do a full rotation. But to trace out this circle, we only needed to go from 0 to pi, as it turns out. So basically, if you see r equals 2 cosine theta, or r equals any constant times cosine theta, you're going to get a circle that looks like this. If instead it said r equals 2 sine of theta, the only difference would be instead of our circle being out oriented along the x-axis, it would be up along the y-axis right here instead. So, hopefully this makes some sense. I would strongly recommend playing around a little bit in Desmos. Desmos will do polar coordinates, and so you can kind of test and play around with some of those graphs. This isn't going to be a class testing you on your ability to graph polar functions. For the most part, I'm going to probably give you the graphs on any exams or quizzes and stuff going forward. But you will need to know kind of the very basics and how to manipulate things. Okay, so now that we've seen these curves, let's do some of that same calculus that we were doing before. I want to talk about, for example, tangents. And I want to do tangents on polar curves. So before we were doing tangents on general curves, I want to do tangents on polar curves. So again, if we have a curve given by r equals some function of theta. So let's stick to ones that are indeed functions. Then what we're going to do is let theta be the parameter of our parametric curve, so that our x, which is equal to r cosine of theta, as you'll recall, can be rewritten as f of theta cosine of theta. So I've simply replaced r with f of theta. R became f of theta. And similarly, y, which is r sine of theta, well, now that's going to simply be f of theta times the sine of theta. And I can write x entirely in terms of theta and y entirely in terms of theta because I have an expression for r entirely in terms of theta. And we now have this written all in terms of one single variable, theta, which is our parameter. Exactly how we had things before. We just are using theta now instead of t. So, to find dy dx, which is the slope of our tangent line, we can use the same approach that we did before. So dy dx is simply going to be dy d theta over dx d theta. But now I have representations for what x and y look like, and so let's figure out what those derivatives look like. So for this one, what is dx d theta? And for this one, what is dy d theta? What are these derivatives? So what is the derivative of x with respect to theta? That's going to be the derivative of this with respect to theta. Well, it's a product of f of theta and cosine of theta. And because it's a product, I need to use product rule when we take our derivatives. So I'm going to get first times the derivative of the second plus second times the derivative of the first. So we'll get first times the derivative of the second. What's the derivative of cosine? It's negative sine plus the second, which is cosine, times the derivative of the first. So f prime of theta cosine of theta. That's what our dx d theta looks like. Similarly for dy d theta, I'll get first times the derivative of the second, which is cosine, plus the derivative of the first times the second. And if I just plug these in to our formula down here, then we get f of theta cosine theta plus f prime of theta sine of theta. There's my dy d theta from right here, divided by dx d theta, which is written right here. I'll write it as negative f of theta sine of theta plus f prime of theta cosine of theta. That is our equation for the tangent. So as an example, if we wanted to find the slope, just to make life easy, let's just find the slope of the line tangent to, let's say our graph is going to be r equals 2 plus the sine of 3 theta at theta equals pi over 4. Okay, so what we're basically saying is that this is my f of theta. That was how we did our definition up here. If r can be written as a function of theta, which is exactly what we've got here, then here's how we define x and y in terms of that f of theta, and here is what that slope will wind up looking like. So for us, our f of theta is equal to 2 plus the sine of 3 theta. And that means f prime of theta, the derivative of this, well, the derivative of the 2 is 0. We don't get anything. But what's the derivative of sine of 3 theta? That's going to be a cosine of 3 theta, but by chain rule, I'll also pick up an extra factor of 3. So I get 3 cosine 3 theta. And so our slope is just dy dx. So we get our slope, which is dy over dx, which is this formula right here. So plugging in, I'm going to get f of theta, which is 2 plus the sine of 3 theta, times cosine of theta, plus f prime of theta, which is 3 cosine of 3 theta, times the sine of theta. There's my numerator, and all I'm doing is copying this formula. So f of theta, cosine of theta, plus f prime of theta, sine of theta, sine of theta. So I've just copied the numerator. I'm going to do the same thing with the denominator. I'm going to get negative f of theta times the sine of theta plus f prime of theta times the cosine of theta. And all I need to do, so this is the general formula for the slope, but we are interested at theta equals pi over 4. So at theta equals pi over 4, then we get a couple of things. We need to know what sine of theta is and cosine of theta, but also sine and cosine of 3 theta. So sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. Sine of 3 pi over 4, which is what we would get when we plugged in theta equals pi over 4 here and here. The sine is going to be also root 2 over 2, whereas cosine of 3 pi over 4 is going to be negative root 2 over 2. Where am I getting these values? From the unit circle. So literally in my mind, got my unit circle here, radius 1, here's x, here's y. Here are the two angles I care about. Here's pi over 4, and this angle to there is 3 pi over 4. This has coordinates root 2 over 2, root 2 over 2. This is the x, which is the cosine. This is the y, which is the sine. And over here, it's negative root 2 over 2, comma root 2 over 2. Again, this is the x, which is the cosine, and the y, which corresponds to the sine when I'm looking at these. So x, which is cosine, is negative. Y, which is the sine, is positive. So there's those values. We just need to literally plug those in and do a bunch of ugly arithmetic. So I've got 2 plus the sine of 3 pi over 4, which is root 2 over 2, times cosine of theta, which is a root 2 over 2, plus 3 times the cosine of 3 theta, so 3 times this one, negative root 2 over 2, times the sine of theta, which is root 2 over 2, over, plugging into the denominator, we will get our negative sign, 2 plus root 2 over 2, times the sine of theta, which is root 2 over 2, plus 3 times the cosine of 3 theta, which is again negative root 2 over 2, times the cosine of theta, which is root 2 over 2. Okay, so these are ugly, but at least they kind of clean up a little bit. When I distribute this through, I will just simply get a root 2. And when I do this times this, I'll get on top a 2, and on the bottom a 4, so plus a half. So 2/4 is the same as a half. And then over here, this is a negative sign. It's a negative 1/2 with a 3, so minus 3/2. And then down here, we'll have a negative root 2 minus a 1/2, and then again, minus 3/2. So on top, this simplifies to root 2 minus 1. On the bottom, I've got negative root 2 minus 2. And we can either leave it like that, or if you want to rationalize the denominator, you need to multiply by the conjugate, which would be positive root 2 minus 2. So we have to just flip the sign of this. So positive root 2 minus 2, positive root 2 minus 2. So we're multiplying by an ugly version of the form 1. The idea is you want to try to do basically difference of squares. And you want the term that's going to basically get canceled here to be this one that involves the roots. We want those to hit each other and get rid of the square roots. So this is, again, just rationalizing the denominator. On top, what do we get? On top, I'll get root 2 times root 2, which is 2. We'll get minus 2 root 2, minus another root 2, so minus 3 root 2. And then negative 1 times negative 2 is plus 2. So that's the numerator. And on the bottom, we get a nice difference of squares. So this times this will be a negative 2. This times this will give me positive 2 root 2. This times this will give me a negative 2 root 2. Those will cancel exactly as we'd hoped. And then negative 2 times negative 2 is plus 4. And so when it's all said and done, we get 4 minus 3 root 2 over, what, 2? And there is our slope. Again, you can also just plug this into a calculator and get out a decimal. That is totally fine. So these are the basics. In the next video, we'll take a look at doing some stuff related to areas and arc lengths of polar coordinates. But at least we've got the basics down here.